Good evening, I'm Alberto Zingaro, and in this poster I present a 3D-0D multiscale computational fluid dynamics model of blood flow in the human heart. This is our joint project with Professor Luca Redè and Alfio Quarteroni, and it is developed at MOX Politecnico di Milano. In the analysis and the assessment of cardiac flows, computational fluid dynamics stands as a tool to complement imaging and experimental techniques, in order to provide a fully detailed description of the flows and also to estimate quantities such as the Walsh stress. We present an accurate multiscale 3D-0D model, which is able to provide a full characterization of the heart's hemodynamic by considering also the valve dynamics, the external circulation, the transition to turbulence, and also a realistic displacement which is provided by the electromechanics. We consider a realistic left heart geometry, and for the three-dimensional model, we model the blood with the incompressible Navier-Stokes equations, but expressed in an ALE framework, in order to account for moving domains. We also model the presence of the aortic and mitral valves by means of the resistive immerse implicit surface method. We discretize this problem in space with the finite element method and with the BDF formula in time with a semi-implicit treatment of the convective term. In particular, we adopt the variational multiscale large eddy simulation method in order to satisfy the in-soup condition, to control the instabilities which arise from the advection dominated regimes, and to account for the transitional to turbulent effects. We prescribe to the left heart displacement which is computed in an electromechanical simulation, and we consider also a lump parameter zero-dimensional closed-loop model of the whole cardiovascular system. We couple the 3D model of the left heart with the zero-dimensional circulation model, and the coupling condition among the 3D and the 0D consists in the computation of the average pressure and flow rates. We numerically solve this coupled problem with a partition numerical scheme, and we first simulate the case of a healthy left heart. And by comparing our results with data coming from imaging, we show that we correctly catch several biomarkers, such as the PV loop, the stroke volume, the EA ratio, the peak systemic pressures and flow rates, and so on. We compare with the echo Doppler data also the shape of the aortic valve and mitral valve velocity, and we also predict the formation of a ring-shaped vortex under the mitral valve section. Finally, we consider the case of a regurgitant mitral valve, allowing us to estimate some clinical indicators and to compare the time average Walsh stress distribution of the left heart with a healthy case, in order to quantify the severity of the examined pathology. Thank you for your attention.